Hello everyone. Today we shall be discussing about the power flow in a three-phase induction motor. Now before going for the power flow, we have to look for the equivalent circuit of a three-phase induction motor. Now a three-phase induction motor under the normal conditions can be assumed as a balanced circuit. It's a three-phase balanced circuit which can be easily represented by a per-phase analysis into a single-phase diagram. The figure here shows the per-phase analysis of a per-phase circuit diagram of a three-phase induction motor. The left-hand portion shows the stator portion, while the right-hand portion shows the rotor portion. Now we have to see that what is actually the power flow, because a lot of conversions and losses are involved while converting the power from the electrical to the mechanical energy. Now, such as if you see in the circuit diagram, we are supplying the circuit a voltage V. That means input power and input electrical power is being given to the motor. Now the input power can be easily represented by a simple three-phase formula that is equal to 3 root 3 VL IL cos phi I, where the cos phi I is the input power factor of the motor. Now as we are using a per phase analysis, it can also be represented in the per phase form as 3 Vp Ip cos phi I. Now Vp and Ip here represent the per phase value. Moreover, when the power enters the stator, is given to the stator, it suffers iron loss and it suffers the copper loss. Now the copper loss is due to basically winding. Now in winding, when the current flows, the winding has got some resistance, due to which there is I square R loss. So basically we can classify that the copper loss is under the category of ohmic loss. Now the stator core is made up of a ferromagnetic material. Now this stator core has got some losses due to hysteresis and eddy current. This hysteresis and eddy current causes the iron loss here, or we can say the core loss here. The remaining power, that is the input power minus the iron loss and copper losses, is transferred to the rotor through the air gap and hence known as air gap power, which is represented by the term PAG. Now if you see that the power is now transferred to the rotor. Now the rotor has also got some windings, so the power will once again suffer the copper loss here, which can be given by I2 square R once again. So it is also under the category of ohmic loss. Now iron loss. The iron losses are not very accountable on the rotor side, because the rotor receives the frequency SF1. Now if the slip is quite low, the current flows in the rotor circuit with a very small frequency, due to which this iron loss is not accountable. Now the remaining power is PMD, which is mechanical power developed. Now when the mechanical power is developed, the power output is not equal to the shaft mechanical power output. Under the ideal condition it has to be so, but mechanical power developed also suffers the losses due to the friction. Now the losses due to friction is basically due to the presence of friction in the bearings. Bearings are used in each kind of motor. It can also be due to the slip ring, which are generally used only in the WRIM, that is wound rotor induction machine. Windage loss. Windage loss is basically due to the contact of the air with the metallic part of the rotor. There is another which losses cannot be accountable, that is stray loss. And the remaining power is actually our PSH, which is shaft power output. Now this power is useful for us, and this is actually the mechanical power we use, or we get at the output of the motor. Getting that into the calculative portion, because in the numericals as well as during the basic fundamentals you have to analyze the condition electrically. So for that we can start with that the input power is equal to root 3 VL IL cos phi I, which is equivalent to 3 Vp Ip cos phi I. Now, iron loss on stator side, let me mention that on stator side is due to the hysteresis plus eddy current on the stator side. Now, copper loss can be given in the circuit diagram. If you see through the circuit diagram, this is my supply power, your power input. Now this resistance R1 signifies the winding resistance here. The power loss here is known as the copper loss on the stator side. This is copper loss on the stator side. Now this RC represents the core resistance. So in this portion there is core loss. That is, copper loss can be given by I1 square R1, where R1 is this resistance. The remaining power, that is input power minus the iron loss minus the copper loss, gives you the air gap power. Now if we go for the per phase analysis, the circuit for the rotor can be given by this thing, by the circuit, where X2 represents the rotor inductance and R2 by S shows the equivalent rotor resistance. Now E2 is the induced EMF per phase. That means the current in this per phase can be given by I2 is equal to E2 upon root of R2 by S whole square plus X2 square. That means the air gap power or the power transferred to the rotor circuit can be given by E2 I2 cos theta 2. Now this is the power which is transferred to the rotor circuit per phase. Now cos theta 2 is nothing. This represents rotor PF. Now rotor PF can be easily given from this equation by R2 upon S upon R2 upon S whole square plus X2 square. If you see that clearly, it is nothing but the resistance of the rotor circuit upon the net impedance of the rotor circuit. Now this is actually the power transfer to the rotor circuit. The power factor of the rotor circuit can be given by resistance of the rotor circuit to the impedance of the rotor circuit. That is, if you see through the figure, R2 upon S represents the rotor circuit resistance, whereas this equation, R2 upon S whole square plus X2 whole square, represents the net impedance of the rotor circuit. That means if we go with PAG is equal to E2 I2 cos theta 2, you will get E2, as I've already discussed, I2 can be represented by this equation. Now this can be expressed further into I2, whereas cos theta 2 can be represented by the equation obtained here, that is R2 upon S upon root of R2 upon S whole square plus X2 whole square. Now if you see this portion, that is this portion, you will get it is E2 upon root of R2 upon S whole square plus X2 whole square, which in our circuit we have already derived that is I2. That means if you say it is I2 square R2 by S. Now if you see through the figure, this I2 square R2 by S. Now this I2 square R2 is nothing but the copper losses occurring on the rotor side. That is, it can be given by PCU upon S, but this would be on rotor side. Now input power is there, copper loss on the stator side, core loss on the stator side, input to the rotor, copper loss, and what left over is, this is mechanical power developed. Mechanical power developed, that means if PMD is equal to PAG minus PCU. If you solve through entire things, that is equivalent to PAG is equal to, formula has already been derived, it is I2 square R2 upon S minus I2 square R2, that is the copper loss on the rotor side. We will come out with I2 square R2 1 minus S upon S. Now if you see that, what it is I2 square R2 upon S into, what is this, PAG into 1 minus S. So we can just come to a relation that if we find out a ratio between what is PAG is to PCU is to P mechanical power developed, it will come out to be 1 is to S is to 1 minus S. Now this is a very important equation because numericals based upon this comes frequently in the AKTU examination as well as in the GATE examination or the other competitive examination. Now the question doesn't stop here. The question further arises, how to determine the torque energy equation. Now if you go through this, you will get it, what you will get, that this entire things that this is a relation between the mechanical power developed, air gap power and the copper losses on the rotor side comes in the ratio of 1 is to S is to 1 minus S. Further, now this mechanical power develops, suffers the friction loss, it suffers the windage loss, and after that, when the mechanical developed power suffers the friction loss and the windage loss, the power left over is known as the shaft power, which is actually the useful power, useful mechanical power. Now we have to see that under the normal conditions, the friction and the windage losses as well as the core losses are considered nearly same, but the ohmic losses are quite variable. The friction and the windage losses are nearly same, but we have to take account one more loss, that is known as stray losses. Now the stray losses is basically the losses which occurs in each and every conductor of the machine, but cannot be measured very exactly, but they account for the 0.5% efficiency, 0.5% efficiency at the full load condition, and the efficiency degrades as the load is changed because the stray losses are on pro rata basis. Now if we are supposed to find out the efficiency, it can be given by efficiency is equal to, in this condition, what is the output? Shaft power, that is PSH. And what is the input? PN. And if you are going to find out the percentage, just multiply that by 100. This is quite easy. Now the efficiency of a general induction motor is always above 85%. You will get nearly 85% efficiency under the normal condition. However, the wound rotor induction motor has got a lower efficiency in comparison to the squirrel cage induction motor because it suffers the losses due to the friction at a highest rate because it has got some slip rings which increases the friction losses and due to which the efficiency is degraded. Thank you. We shall discuss the remaining portions of the induction machine in the subsequent lecture.